Hello everyone. So today we will be starting with the refraction in convex lens. So let us see how this glass material is uh, doing refraction and how the ray of light, how the ray diagrams will be made in this lens. So let us continue with today's class. So as you can see, we have a convex lens here, right? So these are the points. First of all, this is your f1, right? And this is your f2. So one thing I want to tell you is that this distance, let us say this distance is focal length, okay? This distance is equal to focal length. This distance is equal to also focal length, right? And from f1 to f2, this is also focal length. So this is called as the second focus of the lens. Okay, this is also focal length. So from here optical center to this 2f point, this is total 2f. So the meaning is that these 2f1 and 2f2 are your, we call this as the second focus. Okay, this will be present in concave lens also. So that is the thing I want to mention. So you must keep this in mind. Okay, so 2f1 and 2f2 are the second focus. Okay, so now this is your convex lens. So what will happen? Let us consider a ray of light. This is your ray of light, right? This is your ray of light, which is now parallel to the principal axis. And what happens, since you can see that this is your glass, right? This is glass, and in both side of this side, this is air and this is air. So can you tell which is denser and which is rarer medium, right? So always air is your rarer medium when you compare it with glass. So this is your denser medium, right? And again we are having a rarer medium. So what will happen? The refraction of light will be such that, since initially this incident ray is coming from air, which is a rarer medium, and it is going to a denser medium. So at this point of incidence, this is your point of incidence. So at this point of incidence, we will consider a normal like this. You can see that this is your uh, surface. Okay, this is your tangent to this point of incidence. If you draw a tangent, and then this is your normal. So this is your normal at this point. Okay, now what will happen, according to what I told you in last class, is that since this ray of light is coming from a rarer medium, and going to a denser medium, what will happen? It will bend towards the normal. So like this, you can see that it is inclined towards the normal, right? Now again, we have a second interface of medium, second boundary. At this point now, we have a now denser medium, that is glass, and again a rarer medium. Now light is going from a denser medium to a rarer medium. So what will happen? So that we will draw the surface and the normal again. You can see that this is the surface and this is your normal to this surface. So what will happen, since this movement of light is from denser to rarer medium, what will happen? It will tend to bend away from the normal. So like this, you can see that this was your normal. This ray of light, refracted ray of light, has went away from the normal, right? So this is the thing. This is your final refracted ray. So what you have seen, that there are two times the refraction occurs. Okay, what happens is that ray of light, the refracted or ray of light, will be always tend to be towards the denser medium. Okay, you can see that in this at this point, and at this point, what is happening? First there is a rarer medium, so, and there is a denser medium, so it will bend towards the normal. That is, the speed of light becomes less and it is bending towards the normal. Okay, now at this place also, what will happen at the second interface? Since this is a denser medium and this is a rarer medium, it is bending away from the normal. The meaning is that still this ray of light is bending, it is closer towards the denser medium. That is the meaning. Okay, so that is why the denser medium, we say we are having a higher refractive index. Okay, so now we can see that this is how two times there is a change of medium. First time it is rarer to denser, again it is denser to rarer. So in both the cases we have a bending of light. So this is how actually a refraction is taking place in a convex lens. But what happens when we draw a ray diagram, we will directly, we won't show this intermediate, this in between reflection, that is this two times refraction is occurring. Okay, this time this we won't be showing in the ray diagram. We will be directly taking the ray to the center, and then we will be drawing the ray diagrams, because we will be following certain rules for the ray diagram. Okay, so this is how refraction is taking place in convex lens. Now let us see some rules for image formation by convex lens, right? Like we have in mirror, we have also in lens some rules. So what rules are these? Actually, these are nothing but your some standard this is nothing but a geometry part of mathematics. Okay, circles and lines, and that is all we are having here. We have a symmetry somewhere, and if you draw that symmetry, if you consider that symmetry, you will be able to understand how. So this is your parallel line. Okay, that meaning I am saying is that the moment you are drawing the tangents and the normals, and there are triangles and similar triangles and congruent triangles forming, so that is how these rules are getting derived, right? So we just need to know these rules, and we will be perfectly fine, and we will be in a position to draw ray diagrams for all the cases. So listen to these rules, these three rules, then we are all good to go for the ray diagrams. So when these are red colored ones, these are the rays of light which are parallel to the principal axis, right? These rays of light are what? Parallel to the principal axis. And what will happen after refraction? So that is the point I was telling, that now I am, since start refraction will start from here also, but while drawing ray diagrams, we draw directly the direction of the refracted rays. So let us like this. What happens in a convex lens? As I told you in the previous concept also, that ray of light, it is parallel to the principal axis, it will refract in a way such that it will pass through the focus, that is f2. So now one more important thing is here about convex lens is that when rays of light are coming parallel, okay, when incident rays are parallel to principal axis, so they pass through f2. Okay, this is the focus, we call this as focus. This is the definition of focus point for a convex lens. This is the definition of convex, this is the definition of focus point for a convex lens. So always remember that for a lens, always the observer is on the opposite side of the lens. Okay, that is the meaning, right? This is the convex lens, and the observer where will be somewhere on the this side of lens, right? On this side the observer will be, right? And this side the object is placed, that is on the left side of this optical center will be this. On the left side is of this lens, we will be having the object. On the right side the observations will be made. Okay, so we can see that first of all, what you can see, when the rays of light are coming parallel to the principal axis in a convex lens, they are meeting at the point, we call that point as the focus. Okay, this point is the focus, and it is a real focus. Why? Because the rays of refracted ray are actually meeting at this point. That is why this is a real focus. We call it as real focus in a convex lens. Understood the definition of focus? Clear? Now we have a point also, that in convex lens you can see that these rays are coming parallel to this principal axis, and after that they are converging. You can see this is the converging behavior. They are converging like this. Okay, this is called converging behavior. So we can also tell that convex lens sometimes is also referred to as convex lens, is sometimes also called as converging lens. So this is also a term, somewhere you sometimes it is used in place of convex lens. So we call convex lens also as the converging lens, because after refraction the rays of light are converging, that is they are meeting at a point. Okay, and if you are more precise to tell, then the point is point is focus, right? So this is the meaning. So this is nothing but your first law of for rules for image formation of convex lens, that is the rays parallel to principal axis will pass through the focus. The second point we will be seeing. So what will happen? Now this you can see that, like in the center of curvature of a concave or convex mirror, if a ray of light is passing through the center of curvature, they go on the, they retrace back. Okay, they retrace back like this. If this is your incident ray, they will retrace back. So what is happening here? That this is the optical center. This is the optical center. So the rule is that if any incident ray is incident on passing through this optical center, when it passes through this optical center, it will go unrefracted. Okay, it will go unrefracted. That is, it will pass straight away through this lens. So how this is happening? So actually what is happening is that the amount of refraction done by this surface, okay, when it enters, so there one time here the refraction will be occurring, and again the refraction will be occurring here. So what happens? The refraction which is happened in this first interface, okay, in this first interface, it cancels out the second interface. Okay, this is your second interface. So what happens when the, suppose this is your refracted ray, when it enters the lens, and when it exits the lens, it will be in equal and opposite direction to that. So what will happen? Suppose it is like that, it is going like this. Suppose it will bend towards the normal, right? So this is your normal. Suppose it will go, and it will just do like this, okay, and it will do like this, okay, like this. So something like this. So it will just cancel out its first interface. Okay, whatever refraction was happened at the first interface, it will be cancelled out by the second one, and we observe a straight line. So we generally directly draw this straight line, that if any incident ray is passing through optical center, it will go unrefracted. So this is your second rule. The third rule is just nothing but the reverse of the first one. That is, if any ray of light, incident ray of light, is coming from the f1 point, from the first focus, then they will be parallel to the principal axis. So these are nothing but the three rules for the image formation by convex lens. Now let us see the image formation by convex lens. Okay, so convex lens will also have 6 cases. We consider 6 cases in concave mirror. So convex lens, we will be having 6 cases. Okay, so let us consider one by one. First of all, let us say when the object is placed at infinity. So this is your convex lens, and object is placed at infinity. That means that the ray of light are coming from somewhere very far away. So what will happen? These are parallel to the principal axis. They will be meeting at this focus point. So what you can observe is that this is your image point. An image is formed as point sized. Okay, so we can observe that what is happening. If we comment on the nature, location, and image size, the image location is that the focus point, that is the f2, and the nature is what? These rays of light are refracted, and they are actually meeting. So we observe a real image, real and inverted image. I told you that real and inverted go hand in hand. So real and inverted image, that is upside down image, will be formed, and it is highly diminished, that is point sized. Okay, so this is the first case. So this is just like the case of a concave mirror also, in where we place the object at infinity. The image was formed at focus, and it was also real and inverted, and it was also point size. So here also the image is formed, and it is point size. Observe that the image is forming here on the opposite side of the lens. Okay, because I told you the observer will be somewhere here. The observations will be made on this direction, right? This is your observation point, this is your observation side, and on this side you will be observing, and the ray of light are coming from this side. This is a very important point. Next, second case, we have the object is placed beyond 2f1. So now the object is somewhere come closer from infinity to near the lens. So what happens? Let us now consider this AB height. This is your AB point, right? This point is your what? AB point, and this is what? Your object. So what will happen? Now let us draw the incident ray of light. So what happens? This incident ray of light is coming from this object, right? From this object, this incident ray of light is coming. And what happens? This incident ray of light, after refraction, passes through the f2. So that is the first point which we need to consider, right? The second point is, suppose we are drawing this ray of light from again we are considering the second rule. So this ray of light we have taken, so I told you that we need at least 2 rays to make an image. When two refracted rays or two reflected rays, when they intersect, we will consider that point as the image point. So I am taking the two rays from this side, okay, from the top of the object, that is the A point of the object. So A point of the object, I am taking the two rays. So one is passing parallel to the principal axis, one is passing to the optical center, so they are meeting at this point. So I can observe that the image is formed this point, and you can see that this image is upside down. The A point is now downwards, so A dash B dash is your image, it is inverted, it is upside down, and the rays of light are actually meeting. So you can see that when object is placed beyond 2f1, so the image is formed at where, between this second focus and this 2f2 point. So there the image is formed, and it is what, it is real and inverted, it is upside down and it is diminished. You can directly see that this object's size, this image size is less than this object size, so it is diminished case. So next case is when we are placing the object at 2f1. Okay, 2f1 is similar to your when your object was placed at the center of curvature in mirror. So when you are placing this object at 2f1, what happens is that this ray of light, we are considering one parallel to the principal axis and it is passing through the focus. Again, I will consider a second ray of light which is passing through the optical center. It goes unrefracted and meet at this point. So this point is where it is forming an image at, if I draw, this was your top point, so I will mark the top point here only. So I can see that this point your A dash, if this was your A point, this is your A dash point and this is your B dash. So again the image is inverted, but you can observe there is no magnification now. It is of now same size, right? It is of same size, real and inverted. When object is at 2f1, the image is formed at 2f2. So this is similar to your concave mirror case when the object was placed at C. So listen, these ray diagrams are very much similar. So when you talk about ray diagrams, right, when you talk about ray diagrams and nature of image, what happens, convex lens and concave mirror will be going hand in hand, like not hand in hand, like very similar kind of analysis is for convex lens and concave lens, right? And one thing I will tell you earlier, that whether it be a mirror or lens, whether it be a mirror or lens, it doesn't matter. The focal length of a concave thing is negative, and the focal length of a convex, be it a mirror or lens, it is positive, right? So this is the case, because what happens in convex lens, the rays coming to parallel axis are meeting on the focus point, which is on the right hand side of the optical center. So that we will be learning after the sign convention, that on the right hand side of optical center the distances are marked as positive. So that is why the convex lens, we take focal length as positive. So that was the point, right? So for the moment you can see that when the object is placed at 2f1, the image is observed at 2f2. So a similar kind of analysis we can observe in convex lens, like a concave mirror. So next case is when object is placed between 2f1 and f1. So we are bringing the object very far away. Initially it was very far away, and now we are moving the object closer. So what you are observing, that the image is also what it is happening, image is also what happened, image will also move. So in what direction it is moving, we will summarize when we consider all the cases. So you can see again we are considering this ray parallel to the axis, parallel principal axis, passing through the focus point, right? And again I am taking this optical center case. So what happens now, the image is now beyond 2f2. So what is happening, that was I am telling, that when you are bringing the object closer to the lens, the image is going away from the lens. So that is the point. So here also what happens, if the image object distance decreases, the image distance is increasing, right? Now you can see that when the object is between 2f1 and f1, so the image has moved further. But now what has it become, when you move the object further closer from 2f1 point to the lens, the image now starts to become enlarged. You can directly see that the a dash b dash, this length is much larger, right? This is much larger when you compare it with your uh, object size. So image is enlarged, of course it is real and inverted. Now next case we have when the object is placed at 2f1, right? So when the object is placed at 2f1, that means This is your case. This is again I am considering the ray parallel to the principal axis again to the optical center. Now you can see that since this focus point is where the object is placed, these both refracted rays will be going and they won't be meeting in the real world. Okay, that the meaning is that they both are parallel. These two lines are now parallel. So these parallel lines won't be meeting in the real space, but rather we say mathematically that these two rays will be meeting somewhere at infinity and forming an image. So if we are telling that image is forming at infinity, that means since these rays of light are these refracted rays of light are in the observer side and they tend to be meet at infinity. So we call it a real image only. Why? Because these are not the these are not a back trace. You can see that we are not uh, marking these rays of light behind the lens or behind the mirror. Okay, these rays of light are still on the observer side and they tend to meet somewhere at infinity. So what happened, anywhere if you put a screen here, okay, so you can put a screen because this is a real image. If you put a screen, you will observe a very zoomed out image of not the of the object. Okay, very enlarged image of the object at any point wherever you place the screen. Since you observe that very enlarged image on the screen, that is why you say that it is taking on a screen, you are taking image on a screen, so it is a real image only. So that is why this case is what we are considering, that the image location is at infinity but it is real and inverted and highly enlarged. So what is happening to the size of the image? What is happening to the size of image? When you decrease the object distance, the object size is increasing. Okay, that is similar to your concave mirror. In concave mirror also, when you decrease the object distance, the size was increasing. First it was highly diminished at f point, then we bring it beyond c, then it was somewhat diminished, then at c it was same size, then we move it further, then it starts to become enlarged. So meaning was that as the object distance decreases, the size of the image increases. So here also we are observing the same case. When we are moving the object closer to the lens, the image size is getting increased, right? Now let us move to the next case, which is when object is placed between f and o, and this is a very important case, right? Because this case has a direct application, right? So now this is your object which is placed between very close to the lens between f1 and o. So now what happens, this is the ray of light passing through the f2. Again I draw to the optical center, this is going there. Now if you see, after focus point, if the object is present, that is between f1 and o, now these two parallel lines are not parallel anymore now. But what happens in the real space, they are tend to be diverging. So this is going like this and this is going like this. So this is following a path like this. So in the real space, they won't be meeting. That is for sure, right? So what we will do, we will backtrace these lines, right? So what happens, observer on this side, but you can see that if your eyes are on this side, if your eyes are on this side, you can observe that it will appear to your eye that these rays of light are coming from this point, which I marked with the dashed line. Okay, so these rays of light are coming from this point. So we will have an image here, right? So you can see that we can have an image here. We will have an image here, which you can see, which is highly enlarged. Okay, it is enlarged image. And now what about the nature? The nature is now virtual. Okay, now it is virtual, and you can also see that it is erect. It is in upright position as same as the object. So that is why we say that this is virtual and erect, and it is on the same side of the lens we are observing the image now, right? And it is virtual and erect. This is also a similar case to your concave mirror. In concave mirror, you saw that uh, in the last case, in the sixth case, when the object was between F and P, that is, in this case we have optical center. In the mirror, that was pole. So between F and P, if the object was present, In that case only we were having a virtual image. So this is the case in convex lens also, that when object is between f1 and o, in that case only we are observing a virtual erect, and it is enlarged, virtual and erect image, and it is enlarged. So this has a direct application. So this case is used in where? Your magnifying glass, right? In your magnifying glass we are using this, right? So magnifying glass we are using this. So magnifying glass also, and microscope, what is happening there? We are putting the lens very close to the object. We are putting the lens very close to the object, and then we are observing an enlarged image. So suppose for magnifying glass, if we are some person is reading a book, very minute letters are written, so they put a hand lens over there. So what happens? This letters become this much enlarged. So that is, this case is directly you having an application. That's why I told you that this is an important case, right? So convex lens is also used in magnifying glass, microscope. You can understand use also from it. So that is what I was telling. So in magnifying glasses, telescopes, microscopes, projectors, okay, in cameras also, that lens is nothing but your convex lens we are using. And first point, you can see it is used for correcting long sightedness. So long sightedness means what? One who can see only far distances. Okay, long sightedness means only far distances, right? Only far distances are far, not distances. Let us write it more accurately. Far objects are visible, right? So this is the meaning. Only far objects are visible. So what happens? Suppose this is the eye, and this is eye is also having a lens which is convex lens, right? And this is your retina. This is your retina, which acts as a screen where the image is formed, right? So what happens? Suppose due to some reason this long sightedness is what? The only far objects are visible. Suppose what far objects, if the object is very far away, if the rays are coming far away, then the image will be formed on retina. But if the objects are closer, okay, suppose this is a close object, so if the close objects are there, what will happen? This this refraction, this band, this power of lens, this natural lens of eye isn't capable enough of converging this rays closer, coming from closer object to the retina. What it will do? It will instead, the rays of light will be meeting somewhere here. So what we do, in order to correct this, what we do, we place a convex lens. We place a convex lens like this. So what happens? These ray of light now converge further. Partially they converge by this line and partially by this. So then they are actually meeting at the retina and forming an image. So that is how we are using a convex lens in correcting hypermetropia, that is long sightedness. So long sightedness also has another name, we call it as hypermetropia. Now one more thing is that about these defects of vision, right? This is your defects of vision. This is a defect of vision. We call this as defect of vision. There is one more vision which is nearsightedness, and it is corrected by concave lens, which we'll be seeing further. So these defects of vision will be further explained in the next chapter, because we will have a more in-depth analysis on these defects of vision in the next chapter. For just for now, you remember that convex lens is used for correcting long sightedness. Okay, so these are the uses of convex lens. Now let us see the refraction in concave lens, right? So this is your concave lens, I told you. It is now, the curvature now is like this only. Again, you can see that this is your glass, right? This is your glass material. This is your glass material. And this is your air on the both side. This is also air. Here also we are having air. So this is now rarer medium, denser medium, again rarer medium. So what happens is that, suppose an incident ray of light is coming from the air medium. Again I will draw the surface. So this is your surface tangent at this point of incidence. and this is your normal. So what happens? It will move towards the normal. The refracted ray moves towards the normal. Now again at this point we are having glass and air. That is, now this is denser. Now this is rarer medium. So denser to rarer means away from the normal. So we will draw the normals and the surface. This is the surface tangent at this point, and this is the normal. Again we will see that it will bend away from the normal. So what happens is that this ray of light, oh, I told you that observer will be on this side, okay, on the opposite side the observer will be there. So these ray of light is coming, appears to your eye, it appears to your eye that these rays are coming from f1. So you can see that this is how refraction is taking place two times, first at air glass interface and then at glass air interface, similar to what we saw in convex lens. But the thing to observe is that when rays are parallel to the principal axis, this lens is diverging that ray, and it appears to our eye that this ray of light is coming from the focus. So this point is also called as the focus of concave lens, right? Focus of concave lens. So this is your focus of concave lens, and since the ray of light appear to be coming from here, appear to come from at this point, that is why this is called as the virtual focus. This is called as the virtual focus, and you can see this is now defined as the proper focus of a concave lens, and it is on the left side of the optical center. That is why we call that concave lens negative focal length. Okay, that we will be seeing in the sign convention also, but you can understand here also, right? So this is how refraction is taking place in concave lens, and now we will see rules for image formation. So the first one is when the rays are parallel to the principal axis, what happens? I told you that this is how they are refracting away, and if you backtrace these rays, they tend to be meeting at this focus point, which is called as the virtual focus. Now the thing to observe is that when the rays of light were coming parallel to the principal axis, these rays of light, you can see that they are what happens? Diverging. They are diverging. So that is why this concave lens is sometimes called as diverging lens. This concave lens is sometimes also called as a diverging lens, because the refracted rays are diverging. So sometimes if in question they mention a diverging lens is having focal length this, so you need to understand that that lens is concave lens only, right? So this is your first rule. The first rule is that the when the rays are coming parallel to the principal axis, they tend to diverge after refraction. But if you observe, the observer finds that these rays appear to come from this f1 point. That is called the virtual focus. The second law is similar. That is that in the optical center, when the incident ray is made, it will go unrefracted. Next we have image formation by concave lens, right? So image formation by concave lens, we will consider two cases similar to what we considered in the convex mirror. So concave lens and convex mirror analysis is somewhat similar. So when the object is placed at infinity, what happens? The rays are coming somewhere from infinity parallel to the principal axis. So they are diverging in this way, right? And if to the observer, it appears that they are coming from this focus point. So what happens? You can see that they are tend to be coming from this focus point. So these are not meeting in the real space, the refracted rays. That is why the nature of image is virtual and indirect. And you can see that this meeting is at only this point. So this point marks that the image is highly diminished. Rather, it is a point sized image and it is on the same side of the lens. Now when the object is placed anywhere between infinity and optical center. So the object now is placed between infinity and optical center. That means anywhere from infinity to optical center, anywhere you place the object. So how the image will be observed? So you can see that the ray of light is parallel to principal axis. It diverges in a way that it tends to be coming from the first focus point, f1 point. Now if we draw the ray, incident ray, which is going through the optical center coming from that object, you can see that this meeting is here. The ray of light, the refracted ray, if I see this, they are meeting here, and you can see that it is now what happens. You can see that they tend to be meeting at this point. So that is why now we can say that the nature of image is what? Virtual and erect. The nature of image is virtual and erect as it is on the same side of the lens, right? Okay, since one of the ray is what? It tends to be coming from this first focus point, and this ray is like coming from the optical center, and so the observer will see that this back test ray of light will be meeting this ray of light at somewhere behind the lens, and a virtual image will be observed. You can see that the image is erect also. It is upright position AB and A dash B. So this is again the size, you can see that it has been diminished. Now there are certain uses of concave lens, right? So concave lens, first of all, it is used for correcting short-sightedness, which we call myopia. So in myopia, what happens? The person can see nearby objects clearly. They can see nearby objects clearly, but they can't see far by objects. So what happens in this case? Suppose this is the lens of your eye, and then this is your retina. So what happens? The nearby objects there you are able to see clearly. But what happens in a far by object? These rays of light, what happens? They are converging this convex lens, because the eye lens is what? Convex lens. So these rays of light converge before the retina itself, right? Suppose this is the retina. So from far by objects, this refracted ray is meeting before the retina. That's why you can't see far by objects. So what we do? Instead, we place here a concave lens. So you will place a concave lens like this. So what will happen? These ray of light will be somewhat get diverged like this, and when they see this lens, they will be then converging, and so that is how here the image will be formed. So with proper power and proper focal length, these lenses are chosen so that the image is formed at retina. So this detailed analysis we will be seeing in the next chapter, which I already told you. So we will make analysis there. So one more application of concave lens is that it is used in spy hole cameras on doors. That is the small spy hole camera, or you can see spy hole lens. This is you can say spy hole lens. So its spy hole lens is what? In the doors. Suppose this is your door, and sometimes in door there is a eyepiece here where a lens is placed, so you can see from inside who is outside. Okay, who has come outside, who has come to meet you on outside of your house, and you can use this lens to see the person who is standing outside. So this lens is what? Concave lens only. Okay, this is what? Concave lens, because you can see much of the wider area in front of the door. Okay, so that is why convex lens is, and it is also used in combination with other lenses in some optical instruments. So what happens? There are so many so many optical instruments, right? There are laboratory instruments also, and there are also other some complicated instruments which is using combination of lenses and mirrors also. So mirrors, convex lens, concave lens in combination are used. So there is also an use of concave lens. So the major use is this one only. You must always be mentioning this major use of a concave lens. Okay, so this is also asked directly, that in which type of lens is used to correct short sightedness, and which type of lens is used to correct long sightedness. Okay, or myopia or hypermetropia. So you need to understand like this, right? So now we will be seeing the sign convention for lenses. Okay, so now you can see that this is your convex lens, and as I mark, so distances from this side to this side, that is I marked, all this will be what? Negative. And from the optical center to the right hand side, suppose this is your origin, so you consider like this only, and this line is your y-axis, right? So here the distance will be positive, so any distance on the upper side like this, it will be considered height. If I tell specifically, you will be considering height of the object or image. So if height in this direction, you will consider it as positive, right? Height is positive, and in the downside it will be negative. So that is the reason I told you that in a convex lens, in a convex lens, the rays of light were coming like this and they were actually meeting at this point, right? So that is why I told that this is a real focus. And you can see that this focal length is on the right hand side of this lens. So I will take positive focal length for, this is what, convex lens. So for convex lens I am taking positive focal length, and likewise for the concave lens it is on the, it is the virtual focus which is on the left hand side. So that is why the focal length is negative for concave lens. So we will consider a lens formula. So lens formula is nothing but there is a sign difference instead of this plus sign, because mirror formula is what, 1 by f equal to 1 by v plus 1 by u. Instead of that you write just minus. So this is your lens formula, where this is the symbols are having the same meaning, right? This is your focal length, this is your image distance, this is your object distance, right? So I told you that for a concave lens, again concave lens or concave mirror, I will write it now correctly, right? So both concave lens or concave mirror, we are having what? We are having a negative focal length, right? And if it is a convex lens or concave, wait a minute, convex mirror, right? Convex mirror. So there we have what? Positive focal length. So whether it be a lens or mirror, for convex case, the focal length is what? The focal length is what? It is positive. And for concave, whether it is a mirror or lens, the focal length is negative. So that is the meaning, and this is your lens formula. Okay, and I told you, I discussed the question that focal length is fixed. As soon as you make the lens or make the mirror, the focal length is fixed thereafter. Then you will change u, and accordingly image distance will vary depending on this focal length. So this focal length is fixed when you construct a lens or mirror, right? This is your lens formula. So the magnification in lens we will consider. So this is similar to your mirror case, rather just a sign difference here. This formula is what? This formula is similar, that the image size of the image upon size of the object, which is equal to, in this case, listen here, this is v by, right? V by u, not minus v by u. This is important. This is the magnification in lens, which is v by u. Similar case you can consider, m is greater than 1 means, and m is less than 1 and m is equals to 1. So again, if now consider this is your convex lens, right? This is your convex lens, and the image is formed like this somewhere here, right? Somewhere here the image is formed, right? Like this. So, right. So this is your image point here. Here the image is formed. So you can see that m is equals to what? H dash by h. So the image, if it is real, what will happen? Real image is what? It is inverted. So you can see that h dash will be what? Image is what? H dash will be negative, and h will be what? It will always, you will place the object like this. So h is what? Positive. So if it is a real image, what will happen? It is a negative sign. So the sign so the sign, the formula is changed, but our previous analysis is same. Okay. So this is your magnitude. Okay, if magnitude is greater than 1, it means this is a large case, right? This is a large case, this is diminished case, and this is your same size, right? This is your same size. And sign analysis is similar. So m is negative, it means it is a real image, similar to your mirror only. And m is positive, it means it is a virtual image. It is a virtual image, right? How? Because if this is your lens, right? I told you that on the observer side is on the opposite side of lens, where the object is placed. The object is placed on the left hand side and the observer is on the right hand side of the lens. So that's why we have defining this formula as v by u, not minus v by u for lens. This is v by u. Why? because in real image will be on the opposite side of lens. Object will be on this side and the image will be on this side. So what happens in this case, here the V will be positive only and U will be negative. So positive in numerator, negative in denominator means that the magnification is what? Sign you will get as negative, which is indicating that it is a real image. And the moment this V becomes negative, because if the image is virtual, we have seen that the virtual image is on the same side of the lens, so V will also become negative in that case. U is also negative in this case, so M will become positive. So that is why we say that M is positive, means virtual image. So that is the meaning. So this was all about the magnification, uh, lens formula, and discussion on the ray diagrams of concave and convex lens. So in the next class, we will be seeing the numericals related to the refraction involving these concave mirror, convex mirror, magnification, and also we have seen we will be seeing some numericals on refractive index also, which we discussed in the last class. So we will be considering numerical in the next class, and we will be seeing a small topic first, that is power of a lens also in the next class, and we will be winding up the chapter in the next class itself. And thereafter we will be beginning a new chapter, that is continuation to this optics part, which is human eye and the colorful world. Okay, so in the next class we will see one small topic and numericals on this reflection part. So thank you.